So I will first share with you the syllabus information. Okay. This is online at scheduled time. So FOS class, fully online and synchronous. Here's my email, and office hour will be after the lecture, 3:20 to 4:30 p.m. This is a survey course in abstract algebra, introduction to groups, rings, and fields and vector spaces. The textbook is The Gentle Introduction to Abstract Algebra by Professor R. Sethuraman. You can click the link to get the textbook, or you can log into the Canvas and click the Files tab. And I uploaded the textbook there too, so you can download from there. All right. The lectures and quizzes and exams, those are in class, and those are particularly quizzes and exams are through the Canvas. Okay. So I will announce the dates of the quizzes and which material that the quizzes cover on the Canvas. Also, homework and the due dates will be also uploaded as an announcement on the Canvas. Okay. The prerequisite is Math 262 and 320. These are the topics that I will cover throughout this semester. First topic is divisibility in integers, the chapter 1. Right. This was covered in Math 320, so we focus mainly on problem solving in this topic. And also the chapter 1 of the textbook. Second topic is rings and fields. This is chapter 2. So rings and fields will take a lot of time in this course. This through the second week to 8th week. Okay. Third topic is vector space. Vector spaces are covered in the linear algebra, and we're going to relate the linear algebra material with the abstract algebra material. Okay, they are very much related. So, and this is because of that will be briefly covered since it overlaps with the Math 262. So possibly I'm going to spend just 1 week on this vector space topic. Fourth topic is groups. Groups are covered in chapter 4 of the textbook. And this will also take a lot of time, weeks 10 through 15. Okay. The grading plan of this course is 2 in-class exams on October 1st and November 12th, and 2 exams total is 45% of your grade. And there are 6 in-class quizzes, and 1 lowest will be dropped, and therefore only 5 high quizzes will be counted toward your grade, and they are 15%. And also homework, there will be 6 homework assignments, 15%. So I typically make the problems very similar to the homework problems. So you will have to solve the homework problems very carefully and understand how you solve the problems if similar problems given. Okay. And final exam will be December 10th, Thursday, 3 to 5, and final exam will count 25% toward your grade. Okay, so because the class is online and the exams and quizzes are done as an online submission, it is allowed to use any calculator. However, this is a mathematics course and it is mostly about the proofs. Actually, practically, you will not need a calculator to solve any of the problems in this course. So allowing the calculator or not doesn't make a real change. The grades are given as a percentage, 93 and above is A, and so on. Okay. Okay, so you need to check the Canvas frequently since I upload most of the stuffs on the Canvas. I also upload the lecture note. So since the classes are online, I'm going to use this whiteboard feature to solve the problems. Also, I'm going to use this OneNote. Basically, on the OneNote, I copied my lecture notes and so that I can annotate on. So there will be annotations as I go through the notes. Like that. Okay.
I have a question.
Yes.
Will you be posting your notes on Canvas as well or no?
Yes, I will be posting the notes on the Canvas.
Okay, and then you'll be collecting homework once a week or?
It is 6 homework assignments, so it could be it could not be once a week.
Like 3 times every?
Yeah, like once in every 2 or 3 weeks.
Oh, okay. So say if we have questions
Mm-hmm.
from the textbook, because it is a pretty challenging book.
Mm-hmm.
They do take a lot of time.
Mm-hmm.
You're only gonna have office hours for like I think you're only available from 3 o'clock to
3:20 to 4:30.
1 hour.
So 1 hour and 10 minutes.
Oh, okay. Do you have different availabilities or no?
Now you can also email me if you have questions.
Oh, okay, cool. Thank you.
I don't have a different available for office hours. So if you have any questions and you cannot come into the office hour, then you can email me.
Oh, okay.
Yeah.
Yeah.
Professor, I have a quick question about exams.
Yes.
As far as they go, are we going to be scanning and uploading them, or how is that going to be?
Yes. You're going to be scanning and uploading them.
Okay, and are you going to give us additional time to scan?
Additional time will be 15 minutes.
15 minutes, okay.
So 75 minutes for solving problems and additional 15 minutes for scanning and uploading.
Okay, awesome. Thank you very much.
Mm-hmm. Okay. Also read the academic integrity session. And rest of the stuffs. Any questions on the syllabus?
Everyone, will we have quizzes?
When will we have quizzes?
Yeah.
They will be announced 1 week in advance, and they are mostly based on the homework problems.
How many questions we're gonna have on the quiz? It's gonna be for like 10 minutes or 30 minutes?
Quiz, 2 problems. So if it is face-to-face class, I give 20 minutes for completing 1 quiz, so completing 2 problems. But for the quiz, I will give 5 additional minutes to scan and upload. All right. Okay, then I will start today's material. These notes that I'm showing you is on the canvas now. I uploaded a few minutes ago, so you will be able to find it. It is the M320R topic 4, lecture 1. Okay, so this is a part of Math 320 notes that I have taught. All right, since it has a lot of overlaps with the chapter 1 of the Math 360 book. So I will use this note to lecture out of this topic. So it is about the unique prime factorization in the integers. Okay. So before going into any of this, you need to know what primes are. The primes are positive integers greater than or equal to 2, whose only divisors are 1 and
Sir,
themselves.
can you make it bigger because it's really small to see?
It is small to see. I don't know how I can expand this.
That's good.
Yep. Okay. The very important theorems about unique prime factorization is the existence and uniqueness theorem on the prime factorization. So it has two main parts. One part is existence, and the other part is uniqueness of prime factorization. So what is the prime factorization then? Given any positive integers greater than or equal to 2, you break the integer down into products of prime numbers. Okay, that's the prime factorization. And that is, in fact, later we'll prove that it is unique up to reordering. So existence part of this prime factorization theorem states that for any positive integer n greater than or equal to 2 has a prime factorization. There exists a prime factorization. Okay. The proof of this is application of strong induction. So let Pn be a statement of property of n that n is a product of prime numbers. Right?
Can you scoot up just a little bit,
Mm-hmm.
please? Sorry.
Okay. So induction is composed of base step and the induction step. But if we're using the strong induction, the induction step looks like assuming the property for all the previous entries. Okay. In our case, the base step of the strong induction will be the P of 2. What is P of 2? It is a property of 2 that 2 is a product of primes, which is true, right? Since 2 is a prime. Since 2 is prime, P of 2 is true. So base step is done. So for the induction step, we will assume all the previous pi with the I is from 2 through k. And we are now trying to prove the next one for the statement P for the next entry. So k plus 1 is the next entry. we're trying to prove P of k plus 1. So it is case by case. If k plus 1 indeed is a prime, that's the easy case, that P of k plus 1 is true because k plus 1 itself is a prime. That's a product of primes. So that takes care of the trivial case. And case 2 is when the k plus 1 is not a prime. Not a prime. So that the case 1 and case 2 are mutually exclusive cases. Then there will be integers a and b with a is from 2 through k, b is from 2 through k also, such that k plus 1 is a times b. So existence of such integers a and b is because of k plus 1 is not a prime. So k plus 1 must allow a non-trivial divisor. Non-trivial divisor is that it's not 1, it is not itself. So let such integers be a and b, which makes the k plus 1 equals ab. Then our induction hypothesis is that P of A and P of B are true. Okay. We conclude A and B both are products of primes. Okay. Actually, in the induction hypothesis here, what are we using in terms of P of something? P of A and P of B are true. We're using them to conclude A and B are both product of primes. This is A, and this is B. Then k plus 1, which is A times B, can be written as P1 through PS, that is from the A, Q1 through QT, that is from the B. So now, in turn, k plus 1 is a product of primes. It is a product of primes now. Therefore, in this case, 2 P of k plus 1 is also true. So that is the completion of the strong induction. So base step is proved, and the induction step, assuming all the previous steps, the next one also is true. Which means that every integer n greater than or equal to 2 has a prime factorization. Okay. Next, we introduced the Euclidean division algorithm. We did that in Math 320. The statements given integers a and b, here b is non-zero integer. There exist the unique integers q and r, such that r stands for the remainder, so that r satisfies this inequality. It allows 0, but cannot exceed the absolute value of b. It cannot equal to the absolute value of b, strict inequality here, such that a equals bq plus r. Q stands for the quotient. So a can be written as b times quotient plus remainder. And such QR with this requirements should be unique. Here's the proof of uniqueness. If A has two representations as BQ plus R1 and BQ prime plus R2, but both R1 and R2 are remainders, so R1 and R2 must satisfy is inequalities. Okay, but if Q and Q prime are they happen to be equal, then if Q and Q prime are equal, and because of this, how do we obtain this? By setting BQ plus R1 equals BQ prime plus R2. And rearranging the terms, we obtain this identity. If we have Q and Q prime are the same, then R1 and R2 are the same, since the left side of the equality is 0. Okay, so that gives us uniqueness statement for the case of Q equals Q prime. But we may not have that. If Q and Q prime are not the same, then we are going to derive a contradiction. Okay? So if Q and Q prime are not the same, then because of the above identity, and by taking the absolute values, we obtain Q prime minus Q times B can be split up through the absolute value, Q prime minus Q with the absolute value multiplied by absolute value of B. If we are assuming Q and Q prime are not the same, then this absolute value is at least 1. Therefore, we have this quantity is at least the absolute value of B. On the other hand, R1 and R2 are both remainders, so they both satisfy the inequalities. If we take the difference between R1 and R2, they cannot be at least absolute value of B. It should be less than absolute value of B. But that's a contradiction, since we have this quantity is at least absolute value of B, so that's right here, which is supposed to be equal to absolute value of R1 minus R2 by this identity, and that is less than absolute value of B. So we ended up a contradiction of absolute value of B is less than absolute value of B. All right. So that means this if part cannot hold. The Q not equal to Q prime cannot hold. So we must have Q and Q prime are the same. If it is true, then we are guaranteed to have R1 and R2 are the same. So therefore, the division algorithm gives us unique set of integers Q and R satisfying the inequality and the identity here. The next part is the proof of existence. In this Euclidean division algorithm, the existence part relies on the well-ordering principle. Okay. So we apply the following form of the well-ordering principle. Any non-empty subset of natural number including 0 has a least element. The least element means the smallest possible element in the set. So set up the set S as the intersection of the N0 with the A plus BZ forms of integers. So it is all the non-negative integers satisfying x equals A plus BQ for some integer Q. Then we first prove that S is non-empty set. So for this, we need to see that A plus BZ has a non-negative integer. So then if this has a non-negative integer, it has an element in a non-negative integer. So that S is non-empty set. To prove that, we take this integer Q, which is the sign of the integer B. This part is sign of integer B multiplied by absolute value of A. then a plus bq is a plus b times this q here. So that b is cancelled out, and we have a plus absolute value b times absolute value a. But b is observed to be non-zero integer, so absolute value b is at least 1. So this quantity is at least a plus absolute value of a, and that is either positive integer or 0. So it is non-negative. So how do we get this part? If a is negative integer, then absolute value is minus a, so it becomes a 0. When a is positive integer, then this becomes a plus a, so 2a. So positive in that case. If a is 0, then both of them are 0. So in any case, a plus absolute value a is non-negative. So this a plus bq is proved to be non-negative. So we have a plus bz set has a non-negative integer. So as it is, the set S is non-empty set, not equal to empty set, non-empty set. By the well-ordering principle, this non-empty subset of natural numbers with 0 must have a least element. Let's say that is a R. Okay. But we now prove that this R is the desired remainder R in the division algorithm. So we have that R is a non-negative integer since it has to be an element of S. And also R must be less than absolute value of B. So we'll prove this by proof by contradiction. If we assume that R is greater than or equal to absolute value of B, then let's see what happens. Then R minus the absolute value of B is an element of S because it is a non-negative integer by this inequality. And R minus absolute value of B is certainly of the form of A plus B times integer. R is of the form of A plus B times integer. And absolute value of B is certainly it is a B times integer. So R minus absolute value B, it is of the form of A plus B times an integer. But that contradicts the minimality of the R. How is the R defined? It is defined as the least element of the set S. But if R is greater than or equal to absolute value B, then we just found a smaller element in S than the least element of S, which is a nonsense. So that means that we must have this inequality that R is less than absolute value of B. For the existence of Q, by R is in the set S, we must have R is A plus B times integer. So there is an integer Q prime such that R equals A plus B Q prime. So by taking Q equals minus Q prime, we obtain that. Then R is A minus BQ by this. So A equals BQ plus R. Okay. So the expression A equals BQ plus R is satisfied for some Q and R with R is non-negative and less than absolute value of B. The representation of Q and R must be unique because of this argument here. Right? So that's the Euclidean division algorithm. So we proved the existence and uniqueness of the Euclidean division algorithm. But we are still going for the uniqueness part of the prime factorization. We're not done yet. We just did the existence part of prime factorization. This Euclidean algorithm is a preparation for the proof of uniqueness part of prime factorization. Now we turn to the divisibility. We write A vertical bar B, and we say that A divides B. Or B is divisible by A, B is a multiple of A, or A is a factor of B, A is a divisor of B. All of this mean the same thing. And the definition of this is being able to write down the integer B as a Q times the integer A for some Q. Okay. So this is the case R equals 0 in the Euclidean division algorithm. When the remainder is 0, we say the B is divisible by A. So a few examples. The -2 will divide the -6. Since we multiply 3 to this, then we get -6. -2 also divides 6 because we multiply -3 to this, then we obtain the 6. Similarly, -3 divides 6, and 2 divides -6, 3 divides -6, and -3 divides -6. Some trivial consequences are 1 divides any integer n. Since we can write n equals 1 times n. Another trivial consequence is n divides 0 for any non-zero integer n. That is because we can write 0 equals to n times 0. So 0 is divisible by n. The next lemma, what if we have both divisibility conditions, A and B, so that A divides B and B divides A? Then we have A must be either equals to B or equals to minus B. So A equals plus minus B. Secondly, the divisibility is transitive relation. If we have 3 integers A, B, C with A divides B, and this wedge notation is for the logical meaning of and. If A divides B and B divides C, then A divides C. That's the transitive property of the divisibility. All right. So the next definition we need is greatest common divisor. Greatest common divisor of A and B, of 2 integers. And we assume that at least one of them is non-zero. So at least A or B is non-zero. The definition of greatest common divisor is, as the wording suggests, the largest of the common divisors of A and B. That is, there is the largest integer D such that D divides both A and B. This is important part, both A and B. And denoted by GCD parenthesis AB, or just without the GCD, just the A comma B pair, like that. Next lemma is the GCD exists. So we set up the two sets S and T. S is set of all common divisors. A and B. And T is the set of all common positive divisors. Then we need to prove that the T has the largest element. So the largest element in the T will be the greatest common divisor. This is actually the mistake in writing the note. Actually, we don't need the set S. We do not need this. All right. We need to prove that T has the largest element. So note that for any K in T, K must be less than or equal to the maximum of the absolute values of A and B. So let that be capital N. And consider T prime, which is the difference between K and N. So N minus K, with K belongs to T. Then, because of this inequality, N minus K is always non-negative. So it is a subset of natural numbers with 0. All right. Now what we know about the T, trivially, 1 is a common divisor of A and B. So 1 is in T. So N minus 1 is in T prime. Okay. Okay, yes, I will upload the compiled file, which will contain the annotation.
Thank you.
Yep. So N minus 1 is in the T prime. So that T prime is a non-empty subset of set of non-negative integers. Okay. This is a setup for the while ordering principle. So we have the T prime is non-empty and a subset of N0. So it has a least element, small m. So least element means the smallest element in the set T prime. So we have that for any k in T, m less than or equal to n minus k. And also m belongs to T prime. Okay, m is defined as least element in T prime. So m must belong to T prime. We write down m equals n minus d with d in T. So by definition of T prime, it is possible to do so. So m equals n minus d with d in T, and also n minus d is less than or equal to n minus k. And why is this true? It is just rewriting m less than or equal to n minus k with m is n minus d. So then, canceling the capital N and flipping the signs, we obtain k less than or equal to d. Also, d is in T. We already have that. So, what does that mean? For any k in T, k is less than or equal to d. So d is in T, and D is the largest common divisor of A and B. Okay, so GCD is positive for a pair of integers A and B, where at least one of them are non-zero. So now we obtain the existence of the GCD of two integers A and B, with at least one of them is non-zero. So we need just more information than just the existence of the GCD. We actually need to be able to write down the GCD as a linear combination of the integers A and B. So we will do that in the next part. The next part is Badge's lemma. A and B are integers with, let's say, A is non-zero. Then GCD-AB is a smallest positive integer that is a linear combination of A and B. This linear combination is with the integer coefficient. So the set notation of the Badge's lemma is AZ, the multiples of A, in addition to BZ, the multiples of B, equals to GCD of AB multiplied by integers Z. So note that here, AZ plus BZ, this plus notation means the collection of all integers of this form. A times the integer, B times the integer with the addition. The Badge's lemma will eventually prove that this set equals to the set of all multiples of the GCD of A and B. So outlines of proof is divided into 4 parts. The first part is proving that the set S is non-empty set. Okay. Second part is by well-ordering principle. This non-empty subset of natural numbers has a least element D. Third part is proving that the D in the step 2 is actually the GCD of A and B. Okay. Step 4 is the completion part. AZ plus BZ, this set equals to the set of multiples of D. It requires proving the inclusions in both parts. Left side included in the right side, and the right side included in the left side. So we have the set equality. Right, so proof of the first step, the A times A, B times B, it will make the sum of the squares. And obviously that belongs to the multiples of A plus multiples of Z, multiples of B. And since we have A is non-zero, A squared plus B squared is positive. So A squared plus B squared is in the set S. Is in the set S. This shows that the set S is non-empty. Step 2, by well-ordering principle, if we have a set that is a subset of natural number, which is a non-empty set, then it must have a least element D. We call it D. And the step 3 will prove that this D is actually the greatest common divisor of A and B. So first of all, the D belongs to the set S. So the set S, recall the definition of set S, the AZ plus BZ intersection with the natural numbers N. So it must be of the form an plus bn for some integers m and n. Okay. If the d prime is the GCD of a and b, which we know it exists by the previous idea, d prime divides a, also d prime divides b. Therefore, d prime must divide any integer linear combination of a and b. So in particular, d prime must divide d. So giving this divisibility, d prime and d prime divides d. We also need the reverse divisibility. By Euclidean division algorithm, we have a equals dq plus r. We are applying the division algorithm for a and d. So we have a quotient q and a remainder r. The remainder r must satisfy this inequality. Then we may write down the remainder r as a minus dq. The particularly d is a integer linear combination of a and b. So write that integer linear combination down. Then we can factor the a out of this, so that a times a minus m cubed. Then the remaining part is b times the integer minus n cubed. So this remainder is also in the form of az plus bz. Okay. So d is particularly the least element in the set S. Therefore, the R here, it cannot be the least element of the set S, since R is smaller than absolute value of D. D is positive, so absolute value of D equals D anyway, but R is less than D. If this R were positive, what would happen? If R is positive here, it contradicts the minimality of the D. What minimality in particularly? The minimality of being in the set S. Okay, so D must be an element of S and has to be minimal. Since no other positive minimal element possible in the set S, this R must be 0. Okay, that gives us the divisibility. A is D times Q. So D divides A. The similar argument with A replaced by B will prove that D divides B as well. Therefore, D must divide the GCD of A and B, which is defined as D prime earlier. So D divides D prime. Therefore, if the both divisibility conditions hold, then one is plus minus of the other. So D equals plus minus of D prime as a consequence of D divides D prime and D prime divides D. Okay. But both of the numbers D and D prime are positive. Therefore, the minus sign cannot hold. So D must be D prime. So this means that the minimal element we found from the step 2, it must be the GCD of A and B. Step 4 is a completion that D is the smallest possible element in the set S. So we have the integers m and n such that D is an plus bn, the integer linear combination of a and b. Then for any integer z, the multiple of d can be written as integer linear combination of a and b because of this. Okay? So any integer multiple of d is included in the integer linear combination of a and b. We also need the reverse inclusion to prove the equality between these two sets. So for the reverse inclusion, okay, so take element in the AZ plus BZ. So for any m and n in the integers, am plus bn, we are going to prove that this is a multiple of d. But that's quite easy because d was proven to be the greatest common divisor of a and b. So a must be divisible by d, b must be divisible by d. Okay, so putting in a equals dp, b equals dq, and factor out the d. Factor out the d, so we have d times integer expression for any integer linear combination of a and b. So the right side is included in the left side. So we have completed the set equality between the dz and the az plus bz. All right, so the proof is completed. Now, up to here, the GCD exists and the integer linear combination equals to multiples of the GCD. Okay. Corollary 813 here is, if we have two non-zero integers a and b, they are relatively prime. So relatively prime means the GCD equals 1. Relatively prime if and only if 1 is a linear combination of a and b. Having proven the Badge's identity, this should be clear now. If a and b are relatively prime, then GCD-AB is 1 by definition. So 1 is a linear combination of a and b by Badge's lemma. So this is one direction of the statement. It is proving that this is proving the forward implication. If GCD is 1, then 1 is a linear combination. So we need the reverse implication as well. So if 1 is a linear combination of a and b, so say 1 equals ax plus by with integers x and y. And for any integer z, z equals axz plus byz by multiplying z to the above identity. So any integers can be written as integer linear combination of a and b. So az plus bz equals z. So by the Badge's lemma was 812. So GCD-ABZ is the left side. Okay. Well, it has to be the z. So this is that multiples of GCD is the whole integer set. Okay. For example, if this were 2, then left side is even numbers only. So this identity cannot hold. If the GCD is 3, then left side is multiple of 3, so that this equality does not hold. So then the only way that this equality can hold is GCD equals to plus or minus 1. But GCD must be positive, so that GCD should be 1. So the reverse implication also is proved. Okay, next. If two non-zero integers a and b are 0 and they are relatively prime, then prime divisors of a cannot divide b. Also, prime divisors of b cannot divide a. Here is the proof. Let P be a prime divisor of A, and assume that P, the same P, divides B. We're going to derive contradiction. Then P must divide AX plus BY for any integers X and Y, because P divides A, also P divides B. So it must also divide the linear combination of A and B. And since there are X and Y such that 1 equals AX plus BY, by the assumption of relatively prime, we must have P divides 1. A prime number P that divides 1. This is a contradiction because prime number P is at least 2. Okay. Prime number is at least 2, so you cannot divide 1. So that's a contradiction. So the contradiction began when we supposed P divides B. So that must be incorrect assumption. So P cannot divide B. So changing the roles of A and B, we obtain the last sentence. Prime divisors of B cannot divide A. Right? Next proposition, it has a key role in the proof of uniqueness part of unique prime factorization theorem. If a prime number P does not divide an integer A, P does not divide an integer A, so shortly this P does not divide A, we can write this way. Then the GCD of A and P must be 1. A and P must be relatively prime if A is not multiple of P. Here's a proof. Let D be the GCD of A and P, which we know it exists. Then D divides P so that D is 1 or P by definition of prime. Since P is a prime number, only possible divisors of P are 1 or P. As D is a divisor of P, D must be either 1 or P. If D equals P, then P must divide A. Okay, which is impossible because we are assuming P does not divide A. So we must have D equals 1. Therefore, GCD of A and P, D, must be 1. A15. If a prime number P divides AB, where A, B are integers, then P divides A or P divides B. proof of this relies on the previous proposition 814, also Badger's lemma 812. Assume that P divides A times B with a prime number P. If it divides A, then we are done. Since the statement here is P divides A or P divides B, we obtain one of the conclusion, that's okay. So now we assume that P does not divide A, so that will be the non-trivial case. So we should now prove that when P does not divide A, then P must divide B. And the proposition 814, just the previous one, the GCD of A and P is 1. Okay. So at this point, we use the Badger's lemma, the existence of integers x, y, such that ax plus by equals to the GCD of A and P. That is 1. So ax plus by is 1. Since the prime number P divides A times B, there exists an integer k such that pk equals to A times B. So next, we multiply x both sides, particularly this x, obtained from this linear combination. Okay, then pkx equals axb. It's by multiplying x both sides here. But ax is here. But ax is 1 minus py. So pkx equals 1 minus py times b. So rearranging the terms, we can collect everything including p on the one side, pkx and pyb. But then right side only, by this distributing the product here, right side is only b. So that it means that left side can be factored out p. So p times kx plus yb. So it means that b, integer b, equals the prime number p times the integer expression. So we obtain that p divides b. So that's what we desired in the beginning. So our structure of the proof of 815 was by assuming p divides ab. Case 1, p divides a, we are done. Case 2, p does not divide a, we prove that p divides b, so that we are done. The key elements of the proof were the Badger's lemma. And the key elements of the Badger's lemma were the well-ordering principle and Euclidean division algorithm. Okay. Now 817. Prime number p, this is a generalization of the previous statement. If p divides a product of k integers, k greater than or equal to 2, say p divides a1 through ak product, then p divides one of the ai. So we'll prove this by induction on the number of integers multiplied, which is k. So write this property as s of k with k greater than or equal to 2. If p divides the a1 through ak products, then p divides ai for some I. The previous proposition 815, if we have two integers multiplied, then the statement is true. So p of s of 2 is true. Okay. S of 2 is true. For induction step assume that S of k is true for some integer k, and let P divide the k plus 1 integers product. Then split this up two parts, this one and this one. These are two integers now. So applying the S of 2. When the two integers multiply and the prime number P divides it, then either P divides the earlier one or the later one. Okay. So in the latter case, we're done, since P divides one of them, one of the integers listed. In the former case, therefore, if in the former case, P divides A1 through AK product, then by the truth of S of k, when the k integers multiply, then P divides at least one of them. Therefore, P divides at least one of the A1 through AK or AK plus 1. So S of k plus 1 is true. So the induction completes the proof of this 817. So now we are ready to prove the uniqueness of prime factorization. This is a very nice argument. I want you to completely understand this argument. If n is greater than or equal to 2, then the prime factorization is unique. Suppose that we have two listing of prime numbers that ends up as n. So n equals p1 through pk product, also q1 through ql product. And these are prime numbers, p1 through pk and q1 through ql prime numbers. Well, both of them are factorization of n, therefore the product must be equal. And let's call it a star. And focus on the first prime p1. So what do we know about this first prime p1? It is a divisor of the whole product, right? And that whole product is same as the right side. So that P1 divides the right side Q1 through QL product. So there, if that P1 divides Qj, and why is that true? That's because of the previous proposition, corollary 817. If P divides a product of integers, then P must divide at least one of them. So there exists Qj such that P1 divides Qj, but both of them are prime numbers. So P1 and Qj are both prime numbers, but if one of them divides the other, then they must be the same. Okay? So after rearranging the product on the right side, and relabel the Qj as Q1. So we can assume that P1 divides Q1, and because they are primes, P1 equals Q1. So once we have P1 equals Q1, what can we do from the start is canceling the same numbers. Canceling the same non-zero numbers from the identity. So we obtain P2 through PK product on the left side, Q2 through QL product on the right side. And let's label it double star. So remember this procedure of going from the star to double star. Comparing the star and the double star contains just one less prime than the listings of the star. P1, Q1 are removed in the double star. Okay. So now let's say we have the different lengths in the prime factorization. Say K and L are not the same. Then the star to double star reducing step will eliminate one prime at a time from each side and do that until we exhaust one side completely. Okay, if we completely remove one side, finally, then all we have left is just one, the number one, but not the other side. If the lengths of the prime factorization are different, then this canceling step will remove one prime element each time from each side. And whichever side had more prime numbers will still leave the list of the prime numbers multiplied. But the other side is 1. But that cannot happen because product of primes cannot equal 1. So this part gives us that we must have equal number of primes to begin with. K equals L. Then again, back to the reducing step, going from star to double star. Okay. At each time of this eliminating primes, it eliminates one primes each side at each step. So repeating this until we eliminate every prime. Finally, we reach to the point that every primes are eliminated so that there are no prime left in the left side and the right side. So we reach at 1 equals 1. Both sides are now completely eliminated. So at each elimination step, we have equal primes canceled out, right? So by the rearranging and relabeling, Pi must be same as Qi for all I. Okay. So the listing of the prime numbers should be exactly equal to begin with after the reordering. So that gives us the uniqueness of the prime factorization. Okay. So I will stop at this point for today, and I will be including this annotated notes in one PDF and uploading on the Canvas. So this is how I will organize the Canvas. So while this is printing the PDF, I will share the Canvas page. Okay, so this is what you can see in the Canvas Files tab. Notice this Files tab is selected here. So this is the textbook, and these are the 320 review notes, and I covered the first one today. Did I do the second one also? Maybe.
Yeah, you did.
Yes, I did the first one and the second one today. So on the Canvas page again. So we'll create the folder, and the folder will be named after the day of the lecture. So 8-25, so August 25th. Okay. And then here, after this converting to PDF is done, this will be uploaded. Okay. And today, I think I did not use any whiteboard. So I don't have any whiteboard here. So there will be no whiteboard in this folder after this is done. Right.